Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. I'd like to welcome you to the next section in the large data section. This talk is a joint talk. I'm Catherine Van Ingen from the eScience group in Microsoft Research. I'm being joined by my companion Roger, also from the XCG group. We're going to be talking today about some experience we've had over the last year using Azure for science research, really being able to bridge from the desktop, where an awful lot of science gets done these days, to the cloud. Thought I'd start with a little bit of discussion about the data flood. You've seen some of this discussion before earlier this morning in terms of the fourth paradigm. In about 2007, Jim Gray started talking about a fourth paradigm for science. Science moving from experimental science through theoretical science at the beginning of this century. Computational science was really coming of age when I was a grad student, as the advent of large computers made computing modeling viable. Today we're actually living in a data-intensive science world. Very large instruments, a lot of little instruments. Simulation, sensor networks, and interestingly enough, at least in the environmental area, the availability of internet data, the availability to find data that someone else has connected. I spent a lot of my time working with environmental science, and I got to tell you, it's a flood. It's a tsunami. It's the flood of biblical proportion. There's more data out there than I can remember. There's more data out there than any one human can actually use. All of that being said, actually getting science out of the ones and zeros that are out there remains a problem, and it remains a challenge, both in large science, in the astronomy community, in the remote sensing community, and the small communities, even the field science community. It's too hard and too much knowledge as a precursor to beginning. Specialized knowledge, specialized format. Additionally, finding just the right needle, finding that key piece of information that you actually want in this great sea of data remains quite a problem. We've been working at the Berkeley Water Center, sort of triaging the data into three different kinds of buckets, recognizable from a computer science point of view. Remote sensing data, big raster data. It's big, petabytes, right? Not easy to move, esoteric format, esoteric algorithms. Sensors, more and more sensors being deployed. The particular graph there is some USGS data over from the internet. Point-in-time measurements. Key here is the fact that real sensors out in the world don't take nice data. We heard recently about a problem with bees infesting one of the field sites. Ancillary data is a term that we've sort of coined to talk about everything else. Fish counts, algal blooms, and categorical data such as shaded. Very small, very hard to curate, but very, very often the key to understanding the other two. Why make such a decision? Well, for one thing, we've been talking earlier this afternoon about provenance and trust. Provenance and trust varies extremely across those three. Big data from NASA is trustworthy. Little data that I hand to you in a brown bag may or may not be. Data sharing and concerns. The previous session talked a lot about that. Understanding how you feel about sharing your data is very often an emotional question rather than an intellectual question. Lastly, computer science, the tools differ. Most people, I don't know, how many people in this room have used a supercomputer? Okay, so not everybody, right? And yet, some of the problems as it becomes more data intensive are certainly escaping from the desktop. Very, very large computations, and I'll be closing today a little bit with one that we've been working on, takes real engineering. It's not prototype. Anytime you're scaling up an order of magnitude or 3 orders of magnitude, you're going to do more work in avoiding false positives, in handling errors. And lastly, at least in the environmental science, space and time aren't simple dimensions. We all, as computer scientists, think we understand time. Water year is a very common thing used in the United States. The water year begins October 1st. That means that the second month of the year has 30 days. How much software do you think gets upset at 30 days in February? Where does the cloud come into this? Well, the data is a barrier to science. How does the cloud bring that barrier down? First, it brings the resource barrier down. If you can't get to a supercomputer, you can still get to the cloud. If you don't want to go to the complexity of putting up a local computer, you can still get to the cloud. Second is the ability to amortize some work across a number of data sets. Accessing a living curated data set without having to reward a private curator, particularly that graduate student who's leaving and therefore taking the knowledge with them. I particularly am extremely excited about the longer-term potential of clouds, where we can run software as a service. So instead of having to go find an algorithm, download the algorithm, figure out about the algorithm, I can ship my data to the algorithm instead. And lastly, the ability to grow and share in the cloud. So we're not passing data around through FTP sites, but rather moving computations to the data, moving papers and analyses to the data. It really is a potential to enable people today who are locked out of doing a class of science analysis that they'd like to use by breaking down those barriers. And with that, Roger?
Thank you, Catherine. So in this next section of the talk, I'm going to continue on sharing with you our perspective on the role clouds are going to play in research, and also help set context, share with you a little bit about how we set up our data centers, and what is Windows Azure, and in particular, what is Windows Azure in context to other cloud platforms you might be familiar with, enough to make you dangerous so we can move into the next section of the talk and talk about research applications we've built on Windows Azure. So one of the first arguments people will make about the cloud is it's this ability to provision resources on demand, both compute and data. And that simply can't be underestimated when groups simply don't have access to large compute and large data storage. In addition, the more subtle one to actually get your hands on, especially if you're trying to differentiate what Azure offers over infrastructure as a service, is that it's a platform or a framework for deploying your application at scale, scaling it out for you, handling failures, and making it a reliable application as a viable service that you're going to run 24 hours throughout the year. And the one thing we find most appealing is the cloud is really an invisible back end to many of your applications. We would like to extend that into the research domain, where your research applications are able to seamlessly interact with the cloud. But one thing to keep in mind, and it will surface throughout the talk, is today's cloud platforms are really tailored for sharing, photos of cute kittens, handling email. And when we're trying to actually do science applications on these platforms, there is something of an impedance mismatch, but nothing that we can't really program around or build services around. And we'll talk about that when we see research applications on the cloud. There is a spectrum of cloud platforms, and it's worth trying to spend some time, if not here, certainly later, trying to differentiate between what the various offerings are. But we can bucket them, but it's important to note it's a spectrum. At the very low end, I won't call it low end, but one end of the spectrum is infrastructure as a service. When you go to Amazon and get a virtual machine, you're really getting access to hardware and to storage. And there are other cloud providers that are in that bucket as well, where again, you're simply getting access to compute, getting access to storage, you're using VMs as a vehicle for deploying your application on that storage or compute that you're renting. At the other end of the spectrum, we see software as a service, Google Docs, Salesforce.com. What are you getting as you move along this spectrum is you're getting a more customized programming model. Your apps have to fit into a narrower range of functionality, but you get a lot more automated services as well. Windows Azure sits somewhere in between infrastructure and software as a service. It's platform as a service. We're trying to offer an operating system and a framework for deploying your applications in the cloud. And you can, in fact, publish software as a service, and we're abstracting away the hardware, the infrastructure that we're provisioning through being a .NET application. So there's some abstraction going on and some added services as well. We view cloud as basically being an amplifier, an intellectual amplifier for the familiar client services that you have. We think this is a way to actually get over the impedance mismatches, and also you don't have to learn a new platform. I mean, researchers find it, and scientists in particular, find it very difficult to embrace yet another new platform. So our focus throughout our applications is how can we make the cloud a seamless amplifier for your familiar client applications, where, as Catherine pointed out, you may have some data you'd simply like to send it to an analysis service in the cloud. So we're looking at how can we provide analysis as a service, be it SQL or MapReduce algorithms, R or MATLAB. How can we do data visualizations generated in the cloud and brought back to your client software? Again, how can you leverage this compute and storage as an amplifier for tools that you're already familiar with working with? Microsoft's cloud is largely containerized today. It runs a spectrum. We have purpose-built data containers that run from the mega scale, $500 million facilities, 100,000 square foot of servers, basically the size of 10 to 14 football fields, inside of which are going to be these containers. Each container basically has 2,500 servers. The beauty of this is the ability to actually deploy servers at large scale rapidly. If one's ever stood up a data center or a compute center at your university, you know how much time it takes to stand up individual servers. And we'll see in the next few slides just how fast we can set up these 2,500 servers. And in addition is the economics. Not only do you save time for setting up the servers, the management of these servers is highly automated. And the economics of actually operational costs. These servers deliver a PUE, which is basically power utilization efficiency, of 1.2 or even lower. In most university settings, you're seeing PUEs of almost 2. That means every watt of power that comes in for computing, you're almost spending another watt to keep your data center or computer room cool to keep these servers operating efficiently. You're seeing 1.2 for basically containers or these storage facilities that you're going to see here in a second. We're driving those numbers even lower by basically having this container have no air conditioning, just allowing normal airflow to run through it. Hence, we're spending no money on the air conditioning. So again, driving the costs even lower. There's strong economic advantages to this approach of data centers. And in fact, just to illustrate, this is actually a test run of actually standing up a server just to train a team on it. They chose a spot in the parking lot. They get a crane that's basically going to take the container off of the semi-truck when it shows up. There's the container with 2,500 plus servers and power backup, wiring, everything all inside of the server, all inside of the container. They offload it onto a pad. And what you're seeing right there is basically the extent of installing all of these servers. This box is bringing in the internet, bringing in power for the servers, and bringing in a cooling power supply as well. Once those 3 cables are attached, this container is up and running, and Azure starts to install its software and burn them in. And if you look at our Chicago facility, you see what this looks like at scale, where basically we have this nice angular parking for the semi-trucks to back in. There's a little box with the power, the networking, the cooling cables, and within a day, every one of those containers can be up and running. So thinking about how fast you can deploy 24 or 2,500 servers, it's just striking to think that that could be functioning compute power by the end of a day. And these facilities, again, are quite large in size. And we have quite a few of them. Basically, we have over 100 of these data centers scattered around the world, many of which are running Azure. And what's interesting is there's actually been a progression in the architecture, and that's what's striking about how fast this is evolving. Some of our very first centers were, in fact, air-conditioned controlled rooms, all the way up to Dublin, Ireland, which is completely air-cooled. There's basically no air conditioning whatsoever. We're just allowing cool air to run through to cool the servers, all the way to what we're planning our 4th generation server, where there's no shell, there's no container, there's no building. The containers themselves are the actual building, so we've done away with that cost. So it's amazing just how fast this field is evolving. But if we looked inside of one of these data centers, we're going to find Windows Azure. So let's spend a few slides talking about what is Windows Azure. At a very high level, it's really an operating system for allowing you to run your Windows applications in the cloud and scale them out. And in fact, inside of every one of our compute nodes, we have up to 8 cores. One of the first things that Windows Azure does when that container's been plugged in and it's starting to burn itself into one of those machines is it installs a optimized hypervisor to monitor what's going on in the machine and to provide a virtualization layer. On top of that will be the host virtual machine. What you're going to get inside this virtual machine, you can either get between 1 core, or if you say I want an extra large VM, you're going to have 8 cores in your VM. Each one of those is going to have a 1.6 gigahertz x64 processor. You're going to get anywhere between 1.7 gigabytes of RAM if you've just chosen one core. If you chose the extra large size, you'll get 14 gigabytes of RAM. Your fair share of the networking, and then there's some local disk that you're going to have access to. And the VM is going to contain fairly standard .NET Framework, IIS 7.0, Windows Server 2008, and the Azure platform. And these are abstractions that we're going to put on that VM to allow you to get access to storage and get access to compute. So let's look at these two. The computer, the abstraction that Windows Azure provides is you have to break your code apart into two pieces, to factor it into two pieces. The first, you're asked to specify what is your web role. That is, what's going to talk to the outside world and take incoming requests. It's going to be the web service interface, if you will, for your application, and talk to the outside world. Azure will stick a load balancer in front of it, and it will also stick an agent inside of it to monitor the health of your web role. This is where your mainline code is. It goes in something called a worker role. That's where the main is. That's what's actually going to do the computation from the requests coming in from this web role. And you can scale each independently. You may have a very chatty application, a large number of users. You could vary this number between 1 and 100 or 1,000, depending on how much client interaction you expect to have. But you might actually have a very compute-intensive workload. Hence, you'd actually then want to scale out independently the number of workers that stand behind each request. And what's been publicly announced, but we're not going to talk about today in the talk, is something called a VM role. This will basically allow you to take a virtual machine on your local machine, install any software that you have, licenses to, and push that VM role up into the cloud, and then tell us how many instances you want to have running on Azure. So it'll give you much more control over how you actually deploy your applications. There's actually a particular application pattern you're going to see time and time again throughout our demonstrations. Let me just bring up the animation and just walk through it. You will have a web role which will receive work. For all of our science apps, for most of them anyway, we have a web role where the user can upload their data that they want to have analyzed, choose the algorithm they want to have through the web role, and say run. You'll see that work get put into a durable queue. We'll talk in a second about the value of these queues. And behind it, you'll have a farm of workers that will be waiting to pick off work that appears in these queues. And again, if you want to scale independently, you simply add more or less of these depending on the workload that you're trying to do. Very common application pattern and very useful abstraction actually for how to isolate yourself from faults, as we'll see in the blast section I'll talk about. And of course, these queues are actually a very nice abstraction for a number of things, not just for how to build a common application. You can do resource allocation. You could divide your queues by high priority. I'm going to stick 20 workers doing any work that gets put in this queue based on customer ID or urgency of the request. Meanwhile, I have a low priority queue. I only have one worker. It allows you to factor your application based on things like priority. Or you could break your application down into a series of chains of beads. One processing node may need just a few workers. Once it's done, it will put its work in a queue. Other workers will then pick up from that queue. So you can factor your application. It gives you a great deal of latitude on how you actually architect your app. Anybody who's done any work in reliable queues knows that queues are slow, however. There's a cost to be paid for that extra reliability you're getting. Azure also supports TCP communication between workers. So if these workers wanted to have a fast 1 millisecond, 2 millisecond exchange of information with very reasonably high bandwidth, they can open TCP ports between them and exchange them. But again, that communication is not guaranteed to be recoverable, so if a failure happens, you will lose that. Okay. And finally, just briefly, there is an abstraction for storage, and Windows Azure offers you, we've talked about queues, but we also offer the notion of blobs. So if you have pictures or videos or large data sets you want to put into a blob, there's a blob abstraction. And there's different flavors of the blob. And there's tables, which can be thought of not really as relational tables, but think MapReduce or big tables, where you have a key, you have an attribute value, and you have some timestamp, and you can actually put a partitioning field to actually keep them load balanced and clustered together, so that if you touch one, all the others will be basically co-located with it. It's a very nice abstraction for building applications. In addition, there's an abstraction of a disk drive which sits on top of these blobs. So if your application is already writing to a file system or to a disk, it won't have to be changed much. But these are very nice, powerful abstractions on which to build your applications if you're starting from scratch. Okay. Okay, so I've told you a little bit about what you get with Azure. What are the abstractions? How we run it on our data centers. You might say, well, what do you get from all this? What's going to happen on my behalf? What are the background services this platform as a service supposedly offers? So one thing I want to point out is there's this notion of a fabric controller. And it's designed with the fact that this service, if it's running for a long period of time, something's going to happen to it at some point. Either your application itself is going to fail, or if you're running for a very long period of time, the hardware underneath of you might fail. Your application may need to scale because of large demand. So you'd really like to have a fabric which will handle all these cases for you automatically without any special code. And that's really what the Fabric controller in Azure is designed to do. So I'll talk about a couple features of it. Most important, it owns all of the hardware. So when that container backed up and got plugged in, the first thing the Fabric controller did, since it knows the hardware, it will start burning it in and putting it through its paces to make sure it's actually healthy. And then once it's certified, it will add it to the pool of resources, each one of those nodes that it can choose from to stand up an application. Every time one of your applications get running on it, it puts an agent, and it monitors the health as well. And at the moment it starts to think that the health of that application is not 100%, it will start taking some action on its behalf. And when you say, hey, I want to deploy an application, it looks across this pool of resources and says, what's available, what makes sense on where to place this app. We'll talk about a couple twists there. And as it's running both the hardware and your application, it can take prescriptive action to move it around the data center if necessary to ensure your app continues to run. And the Fabric controller, I should point out, is a highly available Paxos cluster, so it's not a single point of failure for your system. One of the things that we provide is this notion of a fault domain, and you'll see it actually in one of our applications in action. Basically, it's trying to avoid a single point of failure. Again, Azure knows the hardware it has in it. If you say, I want to deploy my application, you will minimally get 2 fault domains. It will try to put your instances of your application on orthogonal components of the hardware, all the way from a different rack to a different load balancer to a different switch, basically putting them as opposite ends of the data center as it can. If you say I want 4 or 5 fault domains, it will continue to slice and dice and figure out where to put your application to ensure that if one half of the data center or one rack or one switch fails, your application, some part of it's going to continue to run and service requests coming in from the outside world. You get that automatically. Again, just a few examples, but when you stand up an app, you say, hey, I want 10 front ends across 2 fault domains. So basically, one half the data center could go out, and it's going to continue to run, though the throughput obviously will be affected. The second thing is an update domain. You as a user may actually want to update your service from time to time, and similarly, Windows Azure is going to update their software as well. They need to be able to roll an update through the data center without bringing your application down completely. So a second orthogonal component to this is basically how many update domains to spread your application across. Minimally, you get 2. You could actually specify more. And you could think about this. If you think that there's a long-running computation running against a set of reference data, but that reference data gets updated quarterly, monthly, or weekly, you don't want to stop all the applications or the models that are running. Instead, you'd like to update the data. Anybody coming in new is going to get access to this new copy of the data. Those computations in flight will continue to operate against that old data because they're in another update domain. And only once the behavior is quiesced will they actually get the update pushed onto them as well. And the load balancers will push all new work to the newest updated instance of your service. And so to pull all this together, basically, once Azure, once you've saying, hey, I have an application I want to stand up, Azure will basically allocate the nodes. It will find idle compute nodes that make sense across the entire data center for your application, across different fault domains, across different update domains. It will place the OS on it and images of your code, configure the settings, start up the roles, boot them, configure the load balancers for your application, and then basically monitor in real time your application and make changes if it needs to dynamically to ensure that your application continues to perform. So a lot going on in the background here, much more than what you'd find on your typical cluster. So that's really what you're getting as a platform as a service. So we're going to transition a little bit and talk about a research application. Start of one application, and Catherine will pick up and talk about a second that we've stood up under on Azure. And you can see some of this at work. BLAST is an incredibly well-known application in bioinformatics. It's probably one of the most important software applications, and it's intended to identify the similarity between biosequences. Namely, if we have a biosequence, we'd like to know what it's similar to, or we know some piece of that sequence, we know it performs some function. We may ask a question against all known sequences, what does this relate to? Or what other sequences have this function in it because it matches the sequence? These queries, however, are computationally expensive. It performs a large number of pairwise operations. In fact, a typical sequence query, one query against a database, can take up to 15 minutes. But most workloads are much larger than that. You have an entire body of sequences you want to query against a reference library. And they can take 700 to 1,000 CPU hours. And these reference libraries are growing exponentially. So even if your work is staying the same on what you're comparing at, the background libraries are growing quite fast. And what we're hearing is a lot of researchers, even if they have clusters or had moderate-sized clusters, their ability to run queries against them is basically being outpaced, and they're not able to keep up. You have two choices: either upgrade your cluster or build a bigger cluster. NCBI or EBI have been offering a BLAST as a service. We've had researchers approach us and say, look, that we're trying to run these queries, we're getting kicked off the system. So even small workloads are not able to get through. So a good candidate. The good news is, it's very easy to parallelize BLAST. It's in one of those pleasingly parallel applications. One of the things you could do is you could basically partition the queries. So you have 10,000 or 1,000 query sequences you want to query against a reference database. You can partition that and stitch the results back together again. The database itself, you can actually partition the database and run those queries in parallel and stitch those results back together again as well. So there's multiple levels of parallelization that can take place here. You do have to be careful, though. I mean, a normal database that you're blasting against, a reference database, can be 10 gigabytes. If you tried to run 100 nodes or 100 copies of that, you could very easily exceed a terabyte. And given that the output is 10 to 100 times larger than the input, you could very soon swamp your storage system. So you have to be careful about how you partition this and stand up one of these services. We've implemented something called Azure BLAST, and there's a paper that describes its implementation and some of the stuff I'm going to tell you about today, but we'll talk on some of the high points here. It's a parallel BLAST engine on Azure, freely available. We do query segmentation and data parallel. That is, we split the input sequence, and we're going to send a section of the input sequence to a series of workers. So each one will get its 1/n of the work to be done. And of course, each one of those workers is going to have a multi-core system under it, so it can even split the databases and do its own parallelization once it's picked up a sequence to work on. And when it's done, we merge the results back together again. And this really follows the familiar web role to take the user's input queries, input sequences you want to query against, a queue to put the work into, and we'll break it apart, as you'll see, into those tasks, a sequence of tasks, and then workers that are basically running a local copy of BLAST that will do their bit. And when all is said and done, we stitch the results together again. And there were some special considerations to get this dialed in. We'll talk about just a couple here, but there's more in the paper. One of the first, and this is kind of a busy slide, we'll kind of go through it step by step. It's a simple split join. A sequence of 1,000, 10,000, you're going to see 10 million when we get to it. Query sequences will come in for querying. We will break that up into a number of logical tasks. And the user can tell us how many tasks to break it into. We will give recommendations on what the right size should be. And those tasks will eventually, in the next slide, you'll talk about how we will assign those to workers, to cores. And then we merge it back together. We go ahead and use common NCBI BLAST program is running on each one of our workers. We use the -A switch, which basically says if you're standing under a multi-core machine, go ahead and actually partition the database and run things in parallel yourself. So we'll take advantage of any cores you can stick underneath one of the workers. But you have to think carefully about how big these tasks are going to be. If you put 1 million in it, or you put 100,000 sequences inside of one of these tasks, you could lead to a load imbalance because there's a lot of variability between each one of these individual tasks. One could get done really fast, the other could run for a month. So you kind of want to make it small enough so the variability that might occur between an individual sequence you're querying, the whole job itself is more or less on average balanced across all these. And similarly, you don't want to get it too small because there's unnecessary overheads. NCBI BLAST takes time to start up. You have to transfer the data to that running instance. So again, there's a little bit of right sizing that has gone on here to actually get it at the right size, and the paper talks about that. But the best practice, you really want to run test runs to both profile how much work gets done, set the size, and understand when you're starting to see the overheads from the initial startup being washed out and amortized nicely. There's also the issue of this visibility timeout. We talked a little bit about queues. Queues have this nice feature that if a job fails, your work will be picked up by some other worker node. What controls that is this notion of a visibility timeout. What that says is you're going to put a request in a durable queue, and the moment a worker picks it up and starts working on it, it becomes invisible to everybody else, all the other idle workers. but it's not gone. It's just made invisible. And after some period of time, and you can actually set that time, that work item reappears back in the queue. And what you're trying to control is you're saying, look, the work should have been done within 2 hours. If it doesn't get done, assume that the guy that picked it up has failed and you haven't gotten a failure message, so it should reappear. Somebody else will pick it up. So getting that dialed in is really important. Again, you run a few trials, you understand for a particular task size, the average time, or a bounding time for that is X. Pick X and say, that's my visibility timeout. If it's too small, you're going to see repeated computation, which we did. Too large, and if something does fail, you're idle. You could have picked up that work, somebody else could have picked up that work. Again, we've done some best practices here, and there's a little caveat here about the 2-hour maximum. You basically can send a heartbeat to that message and refresh your timeout period on that. We'll talk about that separately. But with this end-to-end, and then we also did another test. You really want to understand your application. What's the bang for the buck? Do I want to pay for a 1-core really small VM? Is that good enough for me? Or do I want to get the extra large 8-core VM or 12-core when we have it? You can't beat an end-to-end benchmark for your application. So we highly advise doing that. What we've done here, I'll just show you the 2 slides. We actually profiled for Azure Blast. We started up a worker. We varied the number of sequences that were in the work to find out what was the right size, but then we varied the VM, basically an extra large 8-core all the way down to small. And we said, well, how many sequences can you get done per task? We said, well, that small VM is only giving us maybe about 4 or 5 sequences can be accomplished per period of time and measured in sequences per minute. Similarly, we said, how about sequences per dollar? What's the bang for the buck if I really am trying to optimize cost? In this case, and it's not always the case, the extra large both was better bang for the buck and sequences per minute. So it was a no-brainer on what we're going to use. That's not always been the case. There's been cases we've actually found a small VM is the best way to go for throughput, but the cost was not necessarily to the advantage. So we had to make some trade-offs. In this case, it was a win-win to go with the extra large VM. So that's how we set it up. This is the picture. We have a routine that will take the NCBI Blast databases and periodically update an update domain one at a time with the new databases when they're available. We have our splitting code here. We have a web portal that the user can log on, upload the sequences from their desktop, choose the Blast algorithm they want to use, specify what database. That gets registered into a job registry so you can track your job over time to see how it's going. And then we have our scaling engine, which is basically running this splitting task, a scheduler that puts them into queues, and then the user gets to choose how many workers they want to pay for, because that's scalable independently. And these workers will then, when idle, pick up work. When all is said and done, there's a worker role that stitches all your results together and puts it in a blob, and that's where the final result is for the user. Just basically a web service. We have a web role. Basically, you can hit it with Internet Explorer, type in your live ID, and go to town on it. And basically just use your live ID, and you can monitor your job periodically, checking to see how it's doing. We even have in our demo session, it's going on, I think, later tonight, maybe tomorrow, is we have an Excel interface to it as well. If you, again, this client plus cloud, if a lot of sequences are being manipulated inside of Excel, you can actually launch the Blast job from Excel. Okay. Let's talk about some of the performance issues that we saw. Demand was surprising for this. A number of researchers, this group was at the Harwood lab at the University of Washington, is doing biofuels research. They're getting kicked off of the NCBI clusters. There's no shortage of small groups that are actually using Blast to carry out their research and want to have access to a service like this. They were able to complete a job that was basically being booted off of the NCBI servers after 3 days in basically less than a couple of hours, and they got to publish a result on it over a weekend's worth of time. So again, this stuff can actually impact the small end of the science. But let's look at the other end. We wanted to see just exactly how big we could run this. We're actually approached by a research group that actually wanted to do an all-against-all comparison against the non-redundant protein database that has 10 million sequences in it. This hasn't been successfully carried out since the last time the last time it was carried out, there were 2 million sequences in it. Simply having this much compute power is not something most labs have access to. And they're really trying to understand interrelationships between known proteins. What proteins are related to what other proteins? And if so, what functions do they share? What characteristics do they share? And the researchers building a map of these, which looks quite interesting. The actual input database is 4.2 gigabytes. Totally, there's over roughly 10 million sequences, which theoretically could lead to 100 billion sequence comparisons. This is a very compute-heavy job. And we estimated, based on what a local machine would take basically 6.1 years to actually complete this on a dual core machine. We ran a few sample jobs. We actually figured out exactly what it would take to carry this out. And we said, okay, we got a hold of 4,000 cores on Azure. The Azure guys kind of blinked when we asked them for 4,000 cores. They said, we have a European data center which is just coming online, so why don't you move some of that work over to our European data centers since they're setting out, you could help us test it. We basically used 475 extra large VMs, 4 data centers, 2 in the US and 2 over in Europe. We have 8 deployments. What that means is a deployment is basically the data set and it's 1/8 of the share of the number of workers that it's going to run the work on. We basically did a manual divide and conquer where we divided up the sequences, sent them to the different data centers in a blob, and then started up our job. And when load imbalances occurred, we had to redistribute manually. This is one of the more interesting things we found out. As I showed you that spectrum of data centers, our older data centers are actually slower than our newer data centers. Newer hardware, newer networking by a factor of 3. Very surprising. We found ourselves basically shifting work quite fast from the US over to our European data centers, which are about a year and a half newer, simply because of the improvements in the hardware. Well, the end result, 230 gigabytes. 1.8 billion results were out of the result set that are being analyzed right now. Huge result. The job took 10 days of computing, but our estimates it should have been done in 6 to 8 days, so we're like, what the heck happened? Well, one of the messages you're going to take away from this is logs are going to really help you understand what's going on. So let's look at some of that. This is the log records that we generate, start time, executing a task, and then a corresponding ticket ID for that task with an end time and the interval time, how much it ran. And this is what a nice workload should look like. When you see something like this, you know you have a problem. A task started, it never finished, it never completed. How we graph this is for our Northern European data center. There are 62 nodes. Each one of those, again, is an 8-core node. You should see a blue dot saying start of task and a corresponding blue dot saying end of task. If it's red, a failure's happened, and if there's a gap, your VM was sitting there doing nothing, or your node was sitting there doing nothing for some reason. We'll talk about that later. We'll look at this a little bit closer. Here you see a series of errors running through the system. And if you look closer at that and blow that time interval up, you actually see the machines are failing one right after the other. But then they're all automatically restarted at the same point in time. What we're seeing right here is an update domain. All of these nodes are in an update domain. While we were running on this machine for a week, Windows Azure was basically running an update through the system on us. So it wasn't our update, but the actual underlying fabric was changing. And again, that's part of this impedance mismatch. Clouds are really built for sharing photos, doing email. You're in and out. Even if you're doing e-commerce on the cloud, you're in and out with a request. We're running a large science app. We're there for a long period of time, so we're exposed to the kind of updates they're going to be making in the cloud, and they're going to continue to make in the cloud. But the beauty of it was the task just simply came back up and continued chugging away. We did lose a little bit of work, but the fact that it recovered itself is very striking and very telling about what these queues really do work. Similarly, we saw, that was another little nit. Our bad. We actually found that we had some application state that we had persisted somewhere, and when the job came back up, it had picked up that application state and was thoroughly wedged. Again, you have to design for failures when building a cloud system. You keep no state. You start back from fresh, read a queue. Anytime you have system state archived in you somewhere, you're probably going to wedge in a bad way if you get restarted automatically. Again, it takes a little bit of thinking to build these applications to be fault tolerant and scalable. And there's another point that Wei made in the paper is do not rely on barriers on your instances. Because you see this inconsistency in startup times or gaps when somebody's working, if we had written our code so that all 62 nodes needed to be in some state at some point in time, you don't have control over that. So anytime you try to put a barrier or a synchronization point across nodes, you're really at risk that something is not going to come together for you. Again, briefly, moving on quickly, we actually saw a write failure. 35 nodes experienced a blob write failure. Now, we may have been pounding on the same blob in this fabric. It load balances automatically for us. We have not done the forensics to find out what happened here. Azure may have been load balancing on our behalf, spreading those around. But whatever the case was, we hit a fault. And again, all of our nodes failed. Then they all started back up simultaneously. The fabric was taking care of this for us. We really don't know what the fault was, but certainly our fault domain was in fact working, and these were storage writes that we were failing on. And again, we saw an interesting behavior here. We blew that up. We saw a system update happening again. We're familiar with this pattern. We talked to Azure, and they said, it looks like your rack became disconnected for some of these nodes. So again, we're in different fault domains. Some of our work kept going and plugging along. The system recovered automatically once the hardware failure had been recovered from. Again, very interesting to see this and to see the fabric at work for us. Move on here. The one thing I would like to talk about is load imbalance. Many research codes are not uniform in their processing. Based on the sequence you're processing or the model that you're running and the region that you're running, you're going to see variability in the amount of time it takes to run. The same is true for BLAST. What you're seeing is a very dense execution pattern. Work is getting done across all the nodes, and then here come the stragglers. And if you plot utilization, how much work is being done per second, sequences per second, it falls off fairly flat here. And a little more forensics, we actually found that some of these guys were really problematic. They were taking hours and days to process those sequences in that task. And that visibility timeout came back to bite us in the backside because other workers were picking up the same set of data, and we were recomputing the result, and then somebody else would come and recompute. Bottom line is you really want to pay attention to that visibility timeout. If the thing is going to run for 8 hours or 2 days, be careful. It might reappear and somebody else will continue the work. But the most interesting thing was this bounding box. You're renting those cores. This bounding box is what you're paying for. So even though utilization had dropped off down here, you're paying as if all these nodes were idle. Computing. So this is true for any cloud platform today. What you'd really like to have seen is basically only paying for that profile down there. You've rented these things. It's like a hotel room. You're paying for it whether you're in it or not. Separately, I can talk to you about our team is working on a utility that will basically monitor this. When it sees this, it will shut down all of the nodes and restart the jobs only with enough nodes to keep that envelope, that long tail running. But again, that's not something you get from any cloud platform today. But again, for research codes, it's certainly something you want to think about. Will you have a uniform execution? So with that, I'll turn that back over to Catherine to continue with another portion of the talk.
Thank you, Roger. We'll be talking about a slightly different application, in fact, a dramatically different application. But I think you're going to find a number of common themes, common practices. The two groups actually, we talk occasionally, we have coffee, but I think we actually develop the applications pretty much independently, and yet we've come up with some of the same basic learnings. We've been attempting to compute evapotranspiration in the cloud. What's evapotranspiration? Well, it's the release of water to the atmosphere by plants and standing water. If you're interested in, quote, quote, global warming, you're really, really, really interested in climate change, and arguably water is more important than temperature. How do you compute evapotranspiration? Well, for one of the ways is first principles Penman-Monteith. Glorious, ugly equation. Don't try to read it all. The important bits here that I want you to walk away with is one, there's an awful lot of inputs. This is a big reduction calculation. Number two is there's a couple of those inputs in particular, the connectivity terms, which are, well, tricky. In theory, that catchment has a single pixel resistance. In actual fact, determining that, given the variability of the landscape across the pixel, is not so easy. So how are we doing it? Well, we're starting with, for 1 US year, 10 US years, 5 terabytes of imagery downloaded from 5 different sites on the NASA website. NASA maintains the imagery in an FTP site. All you have to do is go get it. Of course, you have to know what to go get, where to go get it, which ones to get, and you have to be very careful not to hit them too hard, because actually at one point we definitely hit them too hard. They keeled over, and like most of the US sites, you want to be backing off and gentle. In order to both compute some of the conductance as well as have verification data, we use the sensor data from FluxNet. Deb talked about that earlier today. There's also some ancillary data, key ancillary data to understand the soil processes, classify the various sites, get to the kind of tree properties. And most recently, we added 3 different data sets, a model synthesis set, climate classification. The vegetative clumping is also a model result. I'll come back to a minute to why we had to do that. Key is handling gaps, okay? Imagery is beautiful stuff, except for the clouds. What did we build? From a computer science perspective, a 4-stage data processing pipeline. Unlike Roger's simple fan out reduce, we're actually in a map, reduce calculation. The data download from the NASA websites, embarrassingly parallel, 600,000 files to download, always parallel. It's a map operation. The reprojection, in order to convert from the NASA format to a format necessary for our computation, is also embarrassingly parallel. It's not one-to-one. One download file does not make one target file. But it is embarrassingly parallel. It's another map operation. The actual science computation, that equation I showed you previously, happens in the derivation reduction stage. Embarrassingly parallel, we're basically going to stack tiles and compute a tile. Finally, and it's something we learned along the way, the 4th stage. The 4th stage is an analysis reduction stage. When you're doing a calculation which is large enough to be tossing around a few terabytes up in the sky and consuming a few hundreds of thousands of CPU hours, it turns out that you actually want a set of science artifacts to understand whether you're getting the right answer. Maps turn out to be a beautiful thing. This thing tells you a lot about whether you're getting the right answer. You want to compute that at scale. You want to compute it in the cloud. You don't want to have to drag down all of your results only to do your mapping. So a lot of the graphs that you'll see, both in our papers and on the website, are actually computed in the cloud because they're computed at scale. How did we build it? Well, similar, as Roger told you, we have a web role and worker roles. In our case, we have one front door web role. It's really the front door for the scientist. And a dedicated worker role, the service monitor role. That monitor role is responsible really for watching our service run. It's kind of, if you like, the brains behind the system. Parses all job requests into tasks. Make sure that if we have to rerun a task because of a fault or other problem, it reruns it. It also does a lot of our other scaling. So it's really the monitor, dedicated monitor. One of the mistakes, by the way, that we made when building it, in retrospect, is that that's a single point of failure. Okay? If we lose the service monitor, we pretty much have to restart the system. All work is actually done by a worker role we call the generic worker. The generic worker, we add, we subtract dynamically to change the number of workers we have going at any time. The generic worker is really dequeuing a task, operating on the task, and then proceeding on. It really is sandboxing the science executable. Our scientists, at least, likes using MATLAB. We use a MATLAB compiler to make an executable. We load the executable up into the Windows Azure platform. But one of the things that means is we want to hide all of the details of Windows Azure from that executable. So we built an infrastructure for sandboxing the science executable. What does it really do? Well, it pulls a task queue. If there's a new incoming task, creates a task log entry, so we know we did something. Stages any application platform files. It goes and gets the MATLAB executable. It makes sure that the MATLAB runtime library is installed on the virtual machine. Stages any input files. For the case of the reprojection, it goes and gets the appropriate tiles that need source tiles. For the case of our ET calculation, it's going to get this stack of other tiles necessary. Any of the files that are in the blobs get put onto the virtual machine in a known location. Starts the MATLAB file. When the MATLAB file is done, takes any of the outputs, puts them back into the blob, then updates the task entry. That way we've got the forensics to know the start, stop, and what was done at all cases. One of the things that means is we can have the scientist use exactly the same development environment on his desktop as appears in the cloud. Any of the errors that might possibly have in the cloud You can find exactly the same way on the desktop without necessarily having the complexity of using a tool that is new. Remember, Roger talked about Excel as the tool and the client being familiar. We believe that that's very, very important. Storage management. We got lots of storage. We recently went on a storage diet, so we're down from 9 terabytes down to, I believe it's 6. But that's over, I think it was 1.5 million files at the peak. In order to not go crazy, we organized our storage really on thematic boundaries. So we have a reprojection, metadata, reprojection, and source storage. Why did we do it that way? Well, because if we have to actually ditch storage for some reason or another, or we have to be concerned in some way, shape, or form, we know where to go look. Just keeping track of all of that. So looking at the reprojection stage in the pipeline, kind of breaking apart the service monitor, you'll find, again, the job status table, path status table, and then these two metadata tables that we had to build in order to do the geospatial tracking. Reprojection needs to know where you are, okay? So common tables, specific tables, necessary to drive reprojection. Why am I making a big to-do about reprojection? How hard is it? I mean, all you got to do is find the nearest pixel, or possibly use a spline. You know, any fool, or at least a second-year grad student, should be capable of doing that. Well, that's true if the data is really, really clean. It's not true in our case, because clouds are just painful. Clouds are big. Clouds last a long time. You can't simply fill through them. You can't simply temporally average through them. They can last long enough that, in fact, filling them becomes variable, science variable specific. It's why we added 2 of those other sets of data, simply to be able to fill for clouds. Another little subtlety that we picked up, we are interested in what is a land surface daytime process. So that means we only care about pixels and tiles that are above the land. That part's easy. You kind of know where the ocean is. But also occur in the daytime. Now, NASA maintains day and night files. But unfortunately, as you might expect, there are the odd occasional times when the satellite is not quite day and not quite night, and you end up with day pixels in night files and night pixels in day files. So again, complication. Our first algorithm had a few bugs, not surprisingly given everything going on. This really, that experience to me is why software as a service in the cloud is going to be so important. I really don't want to have the next scientist I work with have to rewrite that code from first principles, right? Being able to get the various atmospheric products reprojected in a usable form. We showed some simple maps of that at AGU a couple of years ago, and one of the other scientists came up and said, "Can I just have your maps? I don't really want to have to do that reprojection." Reduction service, again, to make the point, they all look the same. Status table, task status table, different storage. Queues and tables, just as Roger explained. How do the pipeline stages interact? We have at all times, as I stand here today, 1 web service deployed, 1 service monitor deployed because it's the monitor, and 5 generic workers. It took us a while figuring out about the 5. We actually have these days a subscription that can get us 250 instances. Running 250 instances overnight is a substantial computer bill. I don't really want to have to do that if we're not really doing anything. But we've noticed that when we actually scale up, it takes up to 45 minutes to bring up to 100 online. So in order to give the turnaround time to our scientists who just wanted to know whether that next computation was going to go, we run 5 at all times, start the calculation while we're scaling up. So we are scaling up and scaling down. When we're done, we scale back down, up, down, at all times. The other thing that we do is download storage in the background. Storage downloading from NASA is not a compute-intensive sort of thing. It's I/O-intensive. So we can run that in the background. So what we really have is a priority system implemented by the combination of the generic worker and the service monitor, which gives priority to downloading in the background or reduction tasks that can be run. If nothing else is going on, we'll attempt to reproject imagery. So responsiveness to the scientist while guaranteeing some forward progress for everyone. We talk about costs with Azure, and I know Marty Humphreys, my colleague that helped build this at UVA, one of the most interesting discussions Marty and I have had is the whole question of cost. You know, why do we talk about cost all the time? What is this cost stuff? Why is cost so much in our face? It's something that we as researchers don't always think about. With Modos Azure, we watched our costs, both in terms of sizing and in terms of where the money went. And I often show young Real and his young daughter, if he had tried to do this computation on his desktop, his daughter would be walking before he finished. Ji Lee is the intern with me last year who did a lot of the work. Our total computer bill is less than the salary I paid him as an intern last summer. So one of the things about Azure is thinking about cost. It is the people, it's our people that's the real cost. Where are we? Pulled this last night from our forensics log, our billing log. You can really see three different, 1, 2, 3 parts of the computation. As the science began to give us good results, we decided to move from continental United States to the FluxNet sites around the world to actually attempting a true global land surface calculation. That really means scaling the computation about a factor of 3, double, kind of for the FluxNet calculation, and it is a factor of 20 to do the global calculation at the same scale. We made the decision that our global calculation was going to be at a reduced spatial scale. We're using 1 kilometer pixels here, 5 kilometer pixels here. One of the things you notice is that if you look at the dark blue, which is sort of the CPU, here's primarily reprojection. Again, our reprojection is well over half. Here, what you see is the light blue and dark blue intertwining. That's the reprojection of the global. Because we've gone to such a larger pixel size, we've moved from CPU intensive to I/O intensive. Okay? Another thing to kind of watch is our storage accumulation. We started in January. I believe we had 2 US years, perhaps 3 US years in the cloud, so we kind of started with a base load. During this period of time, we were uploading the FluxNet sites as well as the remainder of the US sites. We kind of stayed flat for a while with just the FluxNet sites uploaded. While we had run the reprojection, we normally get rid of the source tiles. We don't need them anymore. We get rid of anything we don't need to try and balance our storage. We were being kind of chickened through there. We weren't sure that our reprojection was really working. We weren't really satisfied with it, so we held on to the storage. Here we started actually uploading the global as well as getting rid of some of the early FluxNet. And you could see us hitting almost 10 terabytes until we went on the diet back down to 5, getting rid of the source imagery we no longer need. So one of the things I'd like to sort of point out here is that this calculation changed dramatically over the last 7 months. But our infrastructure just keeps running. That, to me, is the essence of fourth paradigm. Because as the science changes, the compute changes as the data takes you somewhere else. You want to do this? Please.
So just some closing comments.
And this is really some observations a number of our colleagues have been making. You know, clouds really are the single largest computer centers ever constructed. We've tried to show in the talk today they have the potential for both large-scale science and small-scale science. One cannot underestimate the impact of having an economic driver like cloud computing. Every time we've seen a new technology that offers an economic advantage, this has tended to dominate what our computing platforms look like in the future. And we tend to craft our applications, we tend to change how we program to take advantage of these economies of scale and in new technology. So I think it will have a profound impact on how we carry out our science and research. We're fortunate enough to get on board during the early days and maybe have some influence on that. As we've seen, they're very well suited for loosely coupled and data parallel applications, but today tightly coupled low latency applications will perform very, very poorly. We have talks and papers that talk about this separately. A lot of it has to do with the oversubscribed network, the low bisectional bandwidth. Again, clouds are designed for sharing photographs and for storing our email. That's changing. The very fact that we have point-to-point communications today between worker nodes is one sign of the fact that the cloud vendors realize the need to support these kind of workloads, and you can expect to see more. There's papers and technologies called Monsoon that our company has innovated on, and we're now trying to deploy that through our data centers. So expect even the workloads that they can support to change in the future. We like to think of them as an amplifier for familiar client tools, because as Catherine pointed out, programming to clouds right now is far too difficult. And thinking about abstractions of way of integrating them with familiar applications so that scientists don't have to think about that. They're just invoking a service or requesting data from some place, and it just works with their tools. And it's a very healthy ecosystem. Economies of scale, unprecedented. Very healthy commercial ecosystem as a researcher. You're going to have many choices out there. There have been a number of papers talking about certain clouds do certain things very well. You're going to have to learn how to choose which one you'd like to go with. It may not necessarily be Azure. You may find your needs are better suited from another cloud. And a very active research community. That's been very pleasing to see over the last year, the number of venues for cloud computing and research to be surfacing. IEEE, ACM, and other workshops also are appearing. But there is an impedance mismatch, and that's something we tried to communicate a lot during the talk today, is steps you have to take to fit your research application to Azure or to any cloud platform. But that last bullet, they provide very valuable fault-tolerant scalability mechanisms that the grid community has struggled to try to surface a set of abstractions and underlying runtime features to make your applications highly scalable and fault-tolerant.
Thank you.
Oops.
Always forward, Roger.
Try.
So I thought I'd sort of close with what I think of as the three big things we've learned, at least over the last 3 years, and I think both teams have learned them together. And the first is that scaling up and scaling down, the more that you can make the debugging environment the same, the better off you are, particularly since we were developing algorithms as we went. You must plan on reducing down to the desktop. That was the lesson of the fourth stage. If you're going to do a calculation in the cloud, make your graphs in the cloud. Putting all your eggs in the cloud basket definitely means you watch the basket, okay? With 100 instances, and if I just go to sleep, I burn off $288 overnight. It's a pretty good hotel room. There's also a question of where the long-term archive is, and we've started asking that question for Modus Azure in particular, because given that we believe that the reprojected results are actually of interest to a number of other scientists, we're trying to figure out what do we do with that long term? Do we continue to leave them in the cloud? What do we do? I don't know the answer to that. I know it's important to ask the question. And lastly, the thing I've learned is that Azure is definitely a moving target. What you know about it today is going to be different tomorrow. It is changing. It's unlike the grid. It's unlike the grid from fault tolerance. It's unlike the grid in terms of just the programming model being evolutionary, going from the queue, table, blob, to a VM model in the future. And I always like to close with an acknowledgement slide. I really am just an idiot talking head. Those are the people that are actually doing the work with the real ideas. Thank you very much. Can you join me for questions? We have a few minutes for questions.
Thank you. I have a question about the BLAST application. So actually it's two questions. One of them is practically what you show is that if you run your program once every few months, no one will ever need to run BLAST again if you make your results available to the public, if you do all versus all.
I don't believe so, because people are sequencing basically their own, researchers basically have sequenced something which has not been sequenced before. They've got a sample from the ocean. You'd have to, of course, have those entered into the databases and everything like that. Yeah,
so in the next version of the database that you will have, it will be there already.
That's right, if it gets entered into the database. But for those researchers who simply want to actually write a paper on the correlation of certain critters in the ocean, that's not the case. They want to be able to do that on demand.
Okay, yeah. Now what I learned from your example is that if I, as an end user, want to use cloud computing for, say, structure alignment rather than sequence alignment, then I need to wait for an operation like yours to make the program usable in cloud computing, and it's not something I can implement myself. Is this correct?
May I reword that? You're saying if you want to actually get it up and running in the cloud, you have to wait for somebody to actually port it for you?
No, to make the program usable the same way you did with... Could I use BLAST, do all versus all BLAST on the cloud before you implemented Azure BLAST?
Okay, it's a good question there. You could very easily get an individual instance of a program running right now on Azure. But what we're talking about is how to scale it out, how to break the tasks out for you. And that's what's missing on clouds today. That's infrastructure, that's frameworks, application frameworks. That's something our team's working on. The generic worker that Catherine told you about is available. It also performs some of that functionality. And that's really where the computer science research or engineering is going on right now. How can we take any application you have, with a few clicks of a button, you tell us out how you want to scale it out, how to share data between instances, and we will pick it up and then run it in the cloud for you. That's what we're working on today, and where generic worker fits in as well. We can talk more about that if you're later on what the availability of those tools are.
A lot of, again, I think of a lot of that as less specific to Azure per se, and very much specific to scaling anything up.
Yes.
Hi, I'm wondering about some conflicting messages. One of them seems a private cloud may be a good idea for some people. The other says software as a service, which implies more of a shared cloud. And software as a service, BLAST, okay, is stable software. But the idea of software as a service philosophically kills innovation, because means the algorithm will never be redone except by the host or the owner of this cloud, or which is really brings private clouds versus shared clouds versus contribution, open source, all these issues up again if you promote software as a service for scientific research. So I'm wondering what's your comment on that?
And since I may be responsible for some part of that mixed message, let me take that one, okay? I actually think there's two kinds of algorithms, or at least among the kinds of algorithms. There are algorithms that are amazingly stable. BLAST is a great example. A histogramming package, right, from high energy physics, stunningly stable. That kind of algorithm actually can be of great value to the scientists that's coming of age in the digital world, right? Because by nature, it looks like I could write my own, so I start by writing my own. Uh-oh, it got complicated. Gee, maybe I really should go find something, okay? So the class of very simple standard algorithms in the cloud, and while that gets growing and growing in sophistication, that's what I mean by software in the cloud. There will always be cutting-edge research algorithms. I showed you one.
I have a question regarding the effort that you need for putting these two applications on the cloud, because both of these are kind of data-intensive or computing-intensive applications. Let's see how many person hours do you have to put on enable the BLAST on cloud and the Modis processing on the cloud. And if this continues in the future, for example, we need a lot of application for climate, which is also data intensive or computing intensive. Does it mean that for each project we have to do the same or put in the same kind of resource?
Again, let me try and take that one. First, I think it is somewhat labor intensive today. Azure is new. We're still getting our collective heads around what it means. That doesn't mean it has to be labor intensive tomorrow. tools like Roger and like I'm exploring with the generic worker and with the infrastructure for scaling that you're working on, that kind of code is reusable. That kind of code won't have to be roll your own in Azure on the future. So, again, it is changing. We started when Azure was very little. Azure is getting more and more sophisticated. And as we as a computer science community can make more of that grid-like infrastructure available, the easier and easier it's going to get.
So you have tuned the Azure internal structure to fit into these two applications?
No.
Good.
There was a little tuning on what's the right task size, and that was just us. It's any kind of, if you're standing up a cluster, you do the very same thing. How many nodes do I need? How do I factor my application? There is a certain right sizing of the task, but we changed nothing with Azure. We simply use bog standard Azure. And I do believe there is going to be, there is a learning curve. Like Catherine said, we learned how to code these applications just as Azure was being released. So a lot of that was just us learning. Just like if a new multi-core machine comes out, you're going to have to learn how to actually write your application to that. But it's just part of the evolution of programming, I think.
Yeah, I agree.
So in terms of one of your last questions that you had there was a long-term storage or archival aspect. You say you didn't know what to do. I was wondering what some of the questions you had regarding that were. Was it just the budget, if you have 10 terabytes, $1,500 a month, or do you put it off-size? What were some of the questions you had around there? Or, were you concerned that you had a grant for 5 years, so after 5 years it then disappears off the cloud and everywhere else? Or?
Well, I actually work for Microsoft, so I don't have to worry about the grant. To me, the question was kind of twofold. Certainly, price is a question, right? Should we really be paying Azure costs, which are not all that bad, for storage which is inherently cold? Right? There aren't that many people on the planet that really, really, really want a nearest neighbor reprojection of net radiation. Okay? There are enough to make it interesting, but not quite enough. So first of all, the question of cost. Secondly, the question of sort of protection and provenance. We would have to do more work, as has been discussed earlier today here, to really document how did we do it, why did we do it, et cetera, to make the data into truly reusable. Third is the question of just sort of ensuring that the community knows where we are. Right? The NASA sites are well publicized, well documented. The remote sensing community knows that they exist. People are discovering Modus Azure by word of mouth, frankly, and in terms of what imagery we have and things like that, as we're giving science presentations. So it's kind of a question of are we going to be providing, is it the right place? Right? So people will naturally discover it. And I think lastly is the question of long-term archive. Right? Azure is not intended as a long-term archive today. Tomorrow, who knows? It could be changing.
Hi, this is a question about the what you call the fault domain. So if a user wants, can they place different worker roles on different data centers, defining the entire data center as a fault domain across different continents, for example?
Oh, cross data center fault domain, you're asking? At present, no.
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 Okay. So the system assigns worker roles wherever it can find computing?
Yeah, well, you specify what data center you want to run against, and then within that it manages fault domains. You can actually specify, I want to keep my data in this region, I want to run the compute in this region. You can express affinity for certain things, but faulting only happens within one data center.
Okay, and the other clarification is you mentioned the Azure is slightly outside of the PaaS block. Is that because you offer the VM role?
No. I think Azure is in fact spot on platform as a service, and there are other examples of platform as a service, but it's an example of that on that spectrum of clouds.
Okay.
Infrastructure at one end, software as a service at the other.
Yeah.
But Modus, and Blast became software as a service.
Software as a service,
for
absolutely.
Science. Yeah.
Right. So the VM role, could you? I know you said something about public information forthcoming on that.
Yes.
So what kind of VMs can be supported on Azure? Can one run a Linux, operating system or some other VM?
I'll tread on this one carefully. To be clear, what the VM role is the ability for you to install any software that you want on a VM, on a Windows Hyper-V, and it will push the differencing VM up to the cloud, which basically means all the software you'd installed, all the licenses that you had. Separately, they're publishing the protocol for the agent. Remember, the agent is the thing that lives inside of your VM. They're publishing the wire protocol so that your VM, running whatever you want, can talk to the fabric controller and say, I'm healthy, I'm running. In theory, one could push a differencing VM that had Linux on it. As an exercise to the academic community, we'll try that. But that's not what's being pushed, of course. It's just being pushed as a way for you to deploy software. But anybody who's played with Hyper-V knows you can flatten it and put a Linux VM on it and boot it, and you're running Linux on our Hyper-V software. And if you had the agent protocol, you have the necessary pieces to put that VM running whatever OS and talking to the fabric controller so it could start to manage it. But that's not what it's being pitched as.
Yeah, we really intend to use it just as an optimization on the generic worker.
Yep, in a way, you think of VM libraries.
We won't have to load all the runtime all the time.
Yeah.
And there's an awful lot of little executables in their runtime.
Hi, yeah, over here. I just had a question about the generic worker. Is that actually a recommended design pattern, or is that just a way of getting around the lack of dynamic worker instantiation?
The generic worker solves a number of different things. It is a sandbox, right? So that the end user code really cannot tell the difference between running on a local desktop and seeing C:\WAC, user WAC data.
But you could just have dedicated workers for each of the types of work that you require.
We could. We wanted to be able to just schedule fairly simply, so we host anything.
Okay, thanks.
We've also changed the algorithm. The end user algorithm has changed a number of times over that period of time, so it's worked out very well.
Hi, yes. With the idea of software as a service or in general cloud computing, have you seen any resistance from researchers or conflict to analyze, put the data in another place, not in the local server, and running, and have maybe conflicts with confidential or restricted data or other things like that?
Well, for me personally, right, I don't know whether you heard Deb Agarwal's talk earlier. Yeah. The data that would have been concerned there would have been the FluxNet data. Mm-hmm. The paper we're working on is an approved FluxNet paper. Consequently, we had full access to the data. The Motifs data is absolutely in the open public domain. It's on a public FTP site. There's no issue there. That was the only data. It is relatively protected, but we're obeying the appropriate protection.
Okay.
Great question.
Humorous aside and a serious problem, that you've really complicated my search life by talking about computing of clouds and cloud computing, first of all. And second, the serious problem is to follow up on the questions over there. I'm in Canada working with data that cannot be subject to the U.S. Patriot Act. Therefore, I have to make sure that if I'm using cloud computing, it doesn't enter the United States, hence the need to have geographic bounding.
Yes.
Yeah.
That is supported. You can start up a job and you can specify that the data in compute will not leave a certain geographic area, period.
Yeah. Well-known problem in commercial computing.
Does anyone else have any questions?
Well, thank you all very much.
Thank you very much.